See, by name itself, you know that carboxylic acid is COOH group having a carbon with sp3 hybridization. In organic compounds, carboxylic acid were one of the first compounds which were noticed, we can say it as discovered. Okay, that's why most of the carboxylic acid have a common name, or what we call it as the first name. For example, HCOH is a formic acid, acetic acid, 4 carbon is butyric acid, 5 carbon is valeric acid, 2 COH group, oxalic, then malonic, succinic, glutaric, adipic, and pimelic. So you can see all up to 7 carbon atoms. If you compare, we have last one being pimelic acid. Then we have maleic acid. After that, we have fumaric acid. Then we have benzoic acid. This is benzoic acid. If you have 2 COH, phthalic acid. Phthalic acid, based on position, it will have different names. If it is metaphthalic acid, you call it as isophthalic acid. If it is paraphthalic acid, you call it as terphthalic acid. This is an acid which is not having a COH group, also known as barbutyric acid. This is called barbutyric acid. If benzoic acid with NH2 is present, you call it as anthranalic acid. If you have 3 carbon with a hydroxy group, it is called lactic acid. If you have 4 carbon with 2 OH groups, tartaric acid. If you have a total of 5 carbons with 1 OH group here, that is called citric acid. Okay, these are the most common ones. You should know what are their names. Preparation of acids can start from alkanes. Alkanes can be done where you react alkanes in the presence of manganic acetate salts that will convert into acidic group. So methane also converts into formic acid. Alkenes can be prepared into carboxylic acid by using hot and concentrated KMnO4 or hot and concentrated K2Cr2O7. So pi bond will break the bonds here. That will convert into carboxylic acid. Single carbons will always keep oxidizing up to carbon dioxide. If you have multiple carbons, you break it, you get 2 different carboxylic acids. Oxidative ozonolysis is also going to give you carboxylic acid. On breaking this, what is oxidative ozonolysis? Ozone in the presence of peroxide and water. That is oxidative ozonolysis. Next, Koch reaction. Koch reaction is when you have CO in HCl. CO in HCl will have, C, the triple bond O plus and minus, wherein if you have H plus, this lone pair will be taken by this. That creates a positive charge here, and that's when the pi bond will attack. Okay, so that is one way of thinking, correct? Or the same thing can be addressed this way, that pi bond first takes H plus from HCl, creates a carbocation, and the C minus will go attack on this one, and you'll get C double bond O. And then on hydrolysis, we will get an acid form. This is Koch reaction. Alkynes, when you react with O3, you break this bond here, that will convert into RCOOH and R-COOH. So whether you take oxidative ozonolysis or KMnO4, double bond or a triple bond, both will break into acids. Alkyl halides, first we need to convert them into Grignard's reagent. So Rx in the presence of magnesium will convert into RMGX, then treat with carbon dioxide. So R minus will attack on CO2, converts into carboxylate, and that on hydrolysis will convert into acids. Alkyl halide can also be treated with cyanides via SN2 mechanism. So alkyl cyanide will form, and that on hydrolysis will give you amides, which on further hydrolysis will give you acids. Now, this particular mechanism is important for us. Okay, just a second. Right. See, for these two, if you have cyanides in acidic medium or a basic medium, in both cases you will get an acid group. But how the mechanism takes place, check it out. Cyanides, the nitrogen's lone pair first takes H plus, and then water will attack on carbon. That makes it as a double bond form, and the lone pair on this nitrogen will take H plus and convert that into an amide form. Okay. Basically, this will be like an enol form which will convert into an amide form. So amide is an intermediate. Remember that amide is an intermediate. Okay. And amide taking H plus here converts into NH3 plus, and thereafter water attacking here will remove ammonia and get into this acidic group. Ammonia taking away H plus from here converts into ammonium ion and carboxylic acid. This is acid catalyzed mechanism. Girls, you got that? Right. Wherein in the presence of base, OH minus will directly attack, pi bond will shift, you will get N minus. N minus will take H plus, so you will get uh, this particular form, enol type of a form, which on tautomerism will become amide. Okay. Then OH minus will attack on carbon, so you will get this as O minus here. And this O minus, as it pushes towards double bond, NH2 minus is going to come out. But NH2 minus is a very, very poor leaving group. That's why heat is essential in the second case. So when it comes to basic medium, heat should be facilitated so that NH minus can come out. And this NH2 minus will take H plus from here and becomes carboxylate and ammonia. See the difference between acidic medium and basic medium. In acidic medium, you will get ammonium ion. In basic medium, you will simply get ammonia. Please go through the mechanism quickly. Check. Finished? Let's check out. Now we'll take the arene acids, that means benzene based acids. Benzene related acid, which is benzoic acid, can be easily, you know, made out of side chain oxidation. This is toluene. Now, by some means, if at all I oxidize this carbon into acid, that will convert into benzoic acid. And this is easily done by KMnO4 or K2Cr2O7 with H plus and heat. The condition for this is for sp3 carbon. Suppose if you have an sp3 carbon, if benzyl carbon is sp3, this is the first criteria that is important here. Okay. If benzyl carbon is sp3, at least one alpha hydrogen must be present to oxidize to oxidize to oxidize CH3 to oxidize CH3 to COOH group. Okay. So you will notice that there is one alpha hydrogen here. Here there is one alpha hydrogen. Here there is one alpha hydrogen. Okay. So between carbon and hydrogen, oxygen will get inserted multiple number of times so that it can break carbon-carbon bond, carbon-hydrogen bond, eventually get into benzoic acid. Now, if you have it this way, there is one more carbon. So carbon-carbon bond will also break, and this carbon will convert into carbon dioxide. Same way here also, this side it will break. So 2 moles of carbon dioxide you will get. And if you have a double bond, so that means if you already have a double bond, there is no compulsion that it must have a hydrogen. So even if it does not have a hydrogen, we can still get an acid here. So because it is like a simple breaking of double bond group, this side it will become acid, this side it will become carbon dioxide. Okay. So even if you have a triple bond, same logic. Now notice this is sp3 carbon, but without any alpha hydrogen. These are all methyl groups. So if you have a methyl group here without any alpha hydrogen, in that case there is no oxidation happening. Okay. And if you have CH2OH, right, whether it is alcohol, ether, aldehyde, ketone, any form it has, all of them will break down into carboxylic acids, which is benzoic acid in this case. That's clear, beta? Right. If you have two methyl groups adjacent to each other, then they will oxidize. This will all oxidize. This will get oxidation and it will convert into phthalic acid. Likewise, here also if I break it on both sides, you will get benzoic acid plus 2 moles of carbon dioxide. Basically, as you break here and here, you will get this as COH, this as COH. So first what we will get is oxalic acid. Okay, you will get this as COOH and COOH. And if you notice COH and COH with MnO4 minus in acidic medium, you may have learned in redox reaction. Oxalic acid will also convert into carbon dioxide. Manganese will get reduced to Mn plus 2. So that's why first an oxalic acid will form that will get further oxidized to carbon dioxide. Clear, beta? Same way here also the same logic. Here there is one alpha hydrogen. Here there are two alpha hydrogens. So we require at least one, right? So you will break a bond here. You will break a bond here. Make them into phthalic acid, and then I'll get 3 moles of carbon dioxide because this bond also you have to break down. So this carbon, this carbon, this carbon. So all three will become 3 moles of carbon dioxide. Next we have alpha naphthol. This is alpha naphthanol. Okay. So in the alpha naphthol, this is OH group here. So on oxidation, now remember, oxidation is more of a nascent oxygen pushing into the group, correct? A nascent oxygen can be considered like an electrophile. And since it's an electrophile, it will always try to approach the ring which is more activated. Okay, now tell me, between these two rings, which is more activated here, this ring is more activated because there is OH support on it. So the ring which is more activated will always get oxidized. Okay, so that's why. So this ring has this carbon and carbon, isn't it? I mean, sorry, this ring has this carbon and carbon. So that will be the position it will get oxidized. So here and here you will break the bond and you will get this benzoic acid plus, I mean, phthalic acid plus 2 moles of carbon dioxide. Now here there is a benzene and then there is nitrobenzene. Nitrobenzene is a pulling group. So this is less activated and this is more activated. So since this ring is more activated, you can break here and convert that into acids. Clear? So do remember these two examples. That is, more electron donating ring will always get oxidized easily. Okay. Now, if you have a cycloketones, they will also get oxidized to form, both carbons. Like here, you can break it. Basically, you write it in the enol form like this, and enol form can be broken so that this carbon and this carbon will convert into acids. So what are we getting? Adipic acid. So thus we get this as adipic acid. Clear? Next, check out from alcohols. If you have 1 degree alcohol on oxidation, you will get carboxylic acid. If you have 2 degree alcohol, right, with I2 and NaOH, I2 and NaOH will help in making an oxidation wherein this carbon can be removed out and convert into an haloform. So this is an haloform reaction. So through haloform reaction, these two carbons will convert into a carboxylic acid. Here also there is one carbon, so that will convert into iodoform, and rest will convert into acidic group. Even if you have CH3 with I2 and CaOH twice, the logic is the same. Now, first, what would happen? If you take it in the presence of calcium, first the calcium salt will form with CHI3, and calcium salt on dry distillation will convert into acetone. Okay. And here also I2 in NaOH, you can break this bond, converts into this COH and CHI3. Okay. These are all basically iodoform reactions from alcohol. Okay. Next, from aldehydes and ketones, if you recall, aldehydes to acids, we can do it with, KMNO4, K2CR27, toluenes, phalings, Benedict. All of them will help making aldehyde to acids. Correct. While if you have ketonic group, ketone can only be oxidized with KMNO4 and not with toluenes, phalings, and Benedict. Next, check this important reaction. If you have an acid chloride, that can also be converted into an carboxylic acid with an extra carbon, right? So how does this happen? Acid chloride, when you react with diazomethane, that is CH2 minus and N2 plus. CH2 minus and N2 plus, okay? CH2 minus and N2 plus, if you notice, uh, this CH2 minus will attack the carbon first, remove out this chlorine. So you would get this form here, okay? Now once you get this form here, N2 is a good leaving group. That will go. And as N2 is leaving, you will notice that this minus will try to push here. Acha, then how do we get minus here? See, first you get this form here. Then CH2 minus itself will take H plus from the other molecule. You will get minus charge on it. So that minus charge will push here. As it pushes, this carbon is already having a 4 bond. So some bond has to break. So it will break from the alkyl group, and that alkyl as R minus will come and attack here. Okay. And simultaneously N2 will leave. So what is left now? This R, then we have CH, then double bond O. This is the product form. This product is like a ketone with an ene. So that's why it is called ketene. So ketone is called as ketene. Ketone with an ene. Okay. The ketenes has a lot of reactions here. Ketene, when you treat with H2O, okay. So you can have hydrogen getting added here, OH getting added here. So that's how you can get carboxylic acid. Next, ammonia, NH3, H getting added here, NH2 getting added here. Alcohol, H getting added here, RO minus getting added here. Acid chloride, H getting added here, Cl getting added here. So acid chloride will form. Carboxylic acid, H getting added here, COOR will get added here. So you will get anhydride. So this reaction has a lot of advantages because once you get a ketene, you will get lot of carboxylic acid derivatives. Okay. The reaction is known as Ernst-Eisterd reaction. Please go through the reaction. This is the new one. So far, whatever we came, they all came earlier in aldehydes and ketones and alcohols. This is a new reaction. Please go through it once. Finished?
Yeah. So, done, so.
Yeah, sorry, but see now. Check acid derivatives now. If a word derivative is used, okay, derivative means it is like a supplement of a particular functional group. So if you add water to it, again you should get back to that same main functional group. So main functional group in this case is acid, and acid chloride, amide, ester, cyanide, and anhydride. These are all derivatives. Understood what I'm saying? So if you hydrolyze these functional groups, they all will come back to acids only. Okay. So these are called acid derivatives. Now acid chloride on hydrolysis will give acid. Even in basic medium, it will become RCO minus Cl minus, and on H2O it will become again acids. Clear? Carbon monoxide, if you take RO minus will attack on carbon here, correct? And thereafter R will migrate on carbon, and that's how you will get an RCO minus Na plus, and that on hydrolysis will give you acids. Okay. So these are all preparation reactions, and you know that you can always prepare carboxylic acid directly from its own derivatives. Correct? Clear, beta? Right. Next, let's see this. What are the properties of carboxylic acids? So generally, C1 to C9 are colorless liquids and they have pungent smell. And C9 and above are waxy solids and odorless. Okay. And then high boiling point is observed due to inter-hydrogen bonding. Next, it forms dimer in vapor state or in aprotic or non-polar solvent. Any carboxylic acid usually starts getting into dimer form in aprotic or non-polar solvents. Up to carbon 4 simple acids are soluble in water due to strong hydrogen bonding. Benzoic acid is an insoluble in cold water. It will be soluble in hot water. All dicarboxylic acids are solids. Okay, these are some general properties we should know. What are the chemical properties of these acids? Generally, the pK value of carboxylic acid lies between 3.5 to 5.5. Okay, and when we treat with sodium or NaOH or NaHCO3, Na2CO3, this one provides electrons to remove hydrogen as H2 gas. Here it is an acid-base reaction. OH minus will take H plus. Here also HCO minus, HCO3 minus is a base, it will take away H plus. CO3 2 minus is a base, it will take away H plus. And that's how you will get carboxylate ions and respective products. Now here, when you treat with NaHCO3, it is giving a positive, carbon dioxide is forming. So that's why here, what do you say, carbon dioxide is forming. That's why it is a best. Next. When we take acid react with ammonia, this is also like an acid-base reaction. So first salt is formed. Ammonia as a base, this one as an acid. The hydrogen will go here, NH4 plus will form, and salt is formed. As you heat it, it will release out water. So this two hydrogens here and oxygen will come out and converts into amide. So remember, on heating, it will convert into amide. Otherwise, you leave it as a salt. For example, this is a very standard example that is being used. Phthalic acid, when you react with ammonia, first you will get phthalic ammonium salt. That on heating, H2O from here, H2O from here will go away and you'll get amides. This is known as phthalamide. Okay, phthalamide. This is amide. Now, if you heat further, here also NH2 and hydrogen, this will come out as ammonia and nitrogen will link here. So that means you will have a nitrogen with a double bond. This is called imide. Okay, nitrogen with two connections to double bond O and double bond O. This is called imide connection. So the thalamide has now become thalimide. So this is a thalimide. Remember that. This is thalimide. Clear, beta? Thalamide has a lot of applications, so better you remember what is the exact structure. Now, these are some standard reactions of acids. That is, first, dehydration. If I take 2 moles of acids and I take a strong dehydrating agents like P4O10. P4O10 is a very strong dehydrating agent. It can pull away water from it. So as it pulls away, it will convert into an anhydride. Same way here also, H2O, if you pull away, it will convert into an anhydride. This is called phthalic anhydride. This is a regular anhydride. If I take formic acid, OH and H, from here it will come out as H2O and that will convert into carbon monoxide and H2. If you have oxalic acid, you can see this H2O will go away and with concentrated H2SO4, this will convert into CO and this will convert into CO2. So all three will come. Next, if at all I use aluminium phosphate will be responsible to make a decarboxylation here only, OH and H. If you remove that, you'll get a ketene. So aluminium phosphate will result in ketene formation. Okay, dehydration is clear. Now, the reaction which you will see here is about having a single hydroxy group on carboxylic acid. First, starting with alpha position. Imagine I have alpha hydroxy carboxylic acid. And when you heat it, simply heat it, then imagine having 2 moles of this molecule. So in these 2 moles, one molecule has an acid and the other molecule has a alcohol. So those two can dehydrate, convert into an cyclic ester. One above here and one below here. So both way, you will see dehydration will happen and you'll get a cyclic diester. Okay, beta? This is the formation of cyclic diester. Clear? Right. Next. If you have beta hydroxy acid, this was alpha position, no, this is beta position. If you have beta hydroxy acid and heating, then you simply dehydrate it. So that means H from here, or OH from here and H from here can be removed out and make a double bond. So that's how you get an alkene form. So alpha, beta unsaturated acids you will get. Okay. Next, gamma hydroxy acids. Okay. So you will see this is an acid group here, alcoholic group here. So OH and H. If I remove that, we will get 1, 2, 3, 4, 5, 5-membered ring, which is a cyclic ester. If it is gamma, you call it as a cyclic ester, and this is called gamma lactone. Mhm. Cyclic esters are generally called as lactones.
So, but how does
If it
it
is
become a ring?
what, beta?
How does it become a ring?
Third does not become ring. You meant this one?
No, so the gamma hydroxy acid part.
Hmm.
How does that become a ring from an
How does it
ring?
become a ring? See, like this. OH is here. The lone pair from here will attack on carbon. This will go as O minus. Okay. Clear, beta? And hydrogen from here, here, and Here, if you pull it out, what do I get? Water will be out and you'll get a double bond forming. So what is left? Lactone. Okay. Esterification, beta. Basic esterification. This is an acid, this is an alcohol. So what do we get? Ester. Clear? Next. If you have a delta hydroxy acid, so in delta hydroxy acid, oxygen will attack on carbon, OH and H can be removed out, and you'll get delta lactone group. Clear, beta? You'll get this as delta lactone. Now notice this one. If you have epsilon hydroxy acid, okay. Now, if at all it tries to make an ester, it will become a 7-membered ring, which is not very stable form. So, instead of forming an ester now, it would start dehydrating and form a straight chain ester. Okay. So, this OH will react with the next molecules, COOH, and you remove this one. And if you keep on doing it multiple number of times, and as you keep stretching, you'll get an ester linkage here like this. And this ester linkage, as you polymerize, you call it as polyester. So you know that polyester, clothes, right? So they all have polyester bonds. Understood? Right. Next, heating amino acids. Earlier, what we did was heating hydroxy groups. Now let's see what happens if you heat amino acids. If at all I have alpha amino acid, right? Alpha amino acid is at alpha position, I have NH2. Okay. And if I take what we did in these cases now, beta, with OH, what we did, you do exactly same case with ammonia also. Okay. Here, when you had 2 moles at alpha position, if you had 2 moles here, so we dehydrated it, correct? Like this, and you make a cyclic diester. Similarly, here you do the same thing by removing water here and here, here and here. So dehydrate that. So what do we get? We'll get cyclic amides. Okay, clear, beta? So this is called cyclic amides. And cyclic amides are generally called as lactams. These are called lactams. Clear? So you'll get lactam amides. Clear? Next, if you have beta amino acid is this NH2 you remove from H here, alpha position you remove H and you make a double bond. So just like OH, if it has, we did the same thing. You do the same thing with ammonia also. If you have gamma, in case if you have gamma, then lone pair from nitrogen will attack COOH. This OH and H can be removed out and you will get lactam. Okay, clear? And if you have delta amino acid, you see lone pair from nitrogen can attack here. This OH and H can be removed. So you will get again amide. So this is also a lactam. Okay. So one is a 5-membered ring, the other one is a 6-membered ring. Next, if you have epsilon, in case if you have epsilon, then on heating it from this end and this end, if you will polymerize, so you will get this as polyamides. Clear? This time what you get is polyamides. Girls, clear, bacha? Right.
Yes, sir.
Next. Next, if same case, just like we did it for hydroxy, amino, now we do carboxy. That means if you have 2 COH groups, okay. So with respect to this COH, this is alpha position and this is beta position, isn't it? Or rather, I would say at alpha position, I have a COOH group. Is that clear? So or simply call it as beta dicarboxylic acids. So when you have beta dicarboxylic acids on heating, okay, what happens here? Directly one of the CO2 molecule will come out. See how it will take place. If I put this into a structure thoroughly, this COH can be written as C double bond O and H. This COH can be written as C double bond O and H. Okay. Now, as you write that, The lone pair present on this oxygen will take H plus, and thereafter this bond will break here to make a double bond, and carbon cannot hold 5 bonds, so this will break bond with carbon, and this carbon has to make a double bond, so this pi bond will shift on to oxygen. Correct? So this way there is a cyclic rearrangements of bonds, and by which you will notice that this bond is breaking up and this is coming out as carbon dioxide. Correct? This is completely coming out as carbon dioxide. And the rest of the part, if you notice, we have CH3COOH. Now this CH2OH is a enol form. So enol will convert into a keto form. And along with that, you already have a OH group. So what does it get? Acid. So therefore, one CO2 got eliminated from here and acid got formed here. So this is heating of beta di uh, beta diacids. Is this clear? First one. Check out gamma. If you have gamma dicarboxylic acid, okay. So this is alpha, this is beta. At the gamma position, you have COOH. In that case, you just need to dehydrate it. See, this OH and H, if at all I remove it out on heating, you will get a succinic anhydride, because this is a succinic acid. Okay, this is succinic acid. Succinic acid will convert into succinic anhydride. Clear? Right. Next, this one is glutaric acid. This one is glutaric acid. When it comes to glutaric acid, again, remove OH and H from here, you will get a 6-membered cyclic anhydride. So this is glutaric anhydride. Now is the interesting fact here. If by chance you have the next one more extra carbon present here, suppose if at all I only dehydrate, then you will get a 7-membered ring, which is not stable. So that's why in adipic acid, what would happen is that on heating, first acid will go away, and thereafter one carbon dioxide will go away. This will become C minus, and that will attack on this carbon, thus giving out one CO2 out and one H2O out and getting into cyclic pentanone. Clear? What happens with adipic? Apply the same logic even to pimellic acid. In pimellic acid also, first you remove OH and H, then you remove CO2, and this will become minus and attack here. So that will make a 6-membered ring of ketone. Okay. And next, check out decarboxylation reactions themselves. If you have soda lime decarboxylation reactions, okay. If you have a RCOOH reacting with NaOH, acid base reaction, first you will get a salt, okay. And if you put that salt in the presence of calcium oxide, water will be absorbed by calcium oxide, correct? And thereafter, if this salt is being heated strongly, carbon dioxide will come out and this will become R minus. So R minus will come out, I mean, alkyl anion will come out here. So that on taking H plus, which was absorbed by carbon calcium oxide, so R minus will take H plus from there and convert into alkene, and OH minus will be out. So this OH minus and this CO2 will make an acid base reaction to form Na2CO3. So this is the overall reaction. Acid plus NaOH with calcium oxide and heat will give you alkane and Na2CO3. Okay. Now remember, the rate determining step is always the formation of a carb anion. So anything which is making a strong or stable carb anion, in that direction the rate of reaction will be higher. And that's why you will notice if you have NO2, chlorine, they are strongly withdrawing, while methyl, which is strongly donating. Methyl is strongly donating. So if I compare all of them, you see COOH, 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 all of them. If you remove it out, So the carb anion which you are getting here, like this, in that this is the most stable, then chlorine, then hydrogen, CH3 is least stable. Done. This step is called soda lime decarboxylation. We studied this in alkanes only, just repeating it. Hmm. Clear, beta? Next, beta keto acids on heating. See, if instead of an acid here, if you have a keto group at beta position, this is alpha and beta, you have a keto group. That also on heating will release out this carbon dioxide and ends up getting a acetone or ketone in this case. Okay. So here the pi bond will take H plus. This OH bond will break to make a double bond. And from here the bond will convert into a double bond on this side. So that's how you'll get an enol form. And this enol form will convert into a keto form. Okay. And that's how you will get the product formation. Clear? Next is coal-based electrolysis. We have come across this again in alkanes. Acids, when you react with KOH, will convert into salt. Salt on electrolysis will convert into a coupling product of R and carbon dioxide will be removed out. So you can see 2 moles of carboxylate on at anode will release 2 moles of electrons, making 2 moles of RCO dot. And this CO dot will slowly turn into CO2 and come out, and that will be a slow step. And 2 moles of R dot will terminate among themselves to convert into alkanes. So this is coal-based electrolysis. Done. In coal-based electrolysis, if the group is very bulky like this, C double bond O, O dot, carbon dioxide will come and 3-degree radical is forming. It is very rarely observed that 3-degree radicals will terminate to get a product. Instead, whatever the small amount of this 3 degrees form, that itself will combine with a dot here of the next molecule, and that's how you'll get an ester as the major product. Okay, so in this case ester will become a major product. Clear? Next is ipso substitution. Okay, ipso substitution as in, okay, let me rewrite this part, this was a little wrong. Yeah, ipso substitution is removal of sulfur dioxide, sulfuric acid or COOH group on benzene. Okay, so CO, when you have it in dilute acidic medium, benzoic acid will dissociate into these ions. So you will get this as benzene with C double bond O, O minus, with double bond here, and double bond here, like this. Okay, clear, beta? And now, since it is in an acidic medium, it will become H plus. The pi will attack from here, and that's how you will get into C double bond O, O minus, and hydrogen here with a positive charge, double bond and double bond, like this. Okay. Now to retain the aromaticity, right, this bond has to break here. So which means here I need to support it as a double bond, and that means this has to be pushed inside. So thus giving it into the formation like this with hydrogen, and this will become CO2. Done. This is called ipso substitution, guys. Clear now? Next, Hoffman bromide degradation. In this topic, right, this is the most important reaction, and this is a must learn reaction with mechanism, with examples. This is the most important area in carboxylic acids. Okay, so check it out. What we are trying to do is that we are taking a carboxylic derivative. In this case, it is amides. Amides, when you react with 4 moles of NaOH in the presence of bromine and heat, shortcut is this: you just simply remove C double bond O here and join the rest. So what do I get? Primary amines. Amide has converted into amine. Okay. And the C double bond O which we have removed, you react with NaOH and convert into Na2CO3. And rest of the bromine you convert into 2 moles of NaBr. Okay, this is the shortcut. Clear? So short way of thinking is that you just have to pluck out that C double bond O and join the rest. Hmm. Now let's notice how the mechanism is happening. First, you got to realize that amides are generally neutral in nature. Okay, because the hydrogen present on the amides is not sufficiently basic. I mean, sorry, the lone pair present on nitrogen is not sufficiently basic, and this hydrogen is sufficiently polarized. So it is a very, very weak acid as well. That's why OH minus will first extract H plus from here, gets a negative charge on it. Nitrogen carrying a negative charge can act like a nucleophile, attack on bromine and remove out one Br minus. So you will get N-bromoamide. You will get this as N-bromoamide. Okay. And once you get N-bromoamide, this base will again take H plus away, gets a negative charge on nitrogen. That will push here. As it pushes here, the carbon and carbon bond will break and this R will go and attack on this nitrogen. Simultaneously, bromine is a good leaving group. It will leave from here. See, this type of three bonds getting rearranged, right? So this is breaking to become Br minus. This is a new bond making, and this is a breaking to get into R. This is called Wolff rearrangement. This type of bond rearrangement is called Wolff rearrangement. Due to Wolff rearrangement, I will get isocyanate. This product is called as isocyanate. Okay. Once you get isocyanate on hydrolysis, all you need to do is that hydrogen side you give it to nitrogen, OH side you give it to carbon. So this side you will get RNH2 that will be separated out. Okay. And this side you will get carbonic acid which will be separated out. So you can see as a mechanism, you can see that because this has positive charge now, water will attack, pi bond will shift on to nitrogen. And lone pair from nitrogen will be taken by H plus, and thereafter pushing the double bond here, the bond will break from here, ammonia and CO2. Done. Please go through it once. Okay. My recommendation is first you need to read it thoroughly and then try to write and practice once. Okay. Do that now. I can say this. It is a step down reaction. Okay. It's definitely a step down reaction. Step down means one carbon is less, right? Because you are removing out one carbon out of it. Next. Have you noticed something? Bromine was entering first as an electrophile, coming out like a nucleophile, Br minus. Okay. So that is one thing. It enters as electrophile, leaves as nucleophile. Okay. Or enters as Br plus and leaves as Br minus. Okay. The intermediate which is forming in this case is isocyanate. That is the intermediate which is forming. Done. These are a few important points you need to know. What are the limitations of HBD reaction? Okay. In HBD reaction, if this alkyl groups which supposed to be migrate or which supposed to make a Wolff rearrangement is more than 6 carbon, then the rearrangement becomes very slow process. So that means you will not be able to get an amine that easily. Okay. So if it is 6 or more than 6 carbons. Next. If at this alpha position already if there is a halogen, right? And since you are taking an NaOH group, so this halogen will also be replaced by OH first. Okay. And after that you make the entire Wolff rearrangement from here to here. Then you make a isocyanate. Now the problem what happens is as you start hydrolyzing, on hydrolysis you'll get this as amine, right? So up to this the reaction should be completed, but it won't. Reason being carbon carrying two lone pair carrying groups. Then oxygen will push it, try to remove NH2 minus. And NH2 minus will take H plus and convert that into ammonia. And what you get is an aldehyde. So you're not getting an amine, you're actually getting an aldehyde. So this is a disadvantage. Clear? So at alpha position, we should not have either OH or we should not have either halide. Okay. Third case, if alpha position is a triple bond. Okay. Again, you do all the same things, all necessary things to be same. You go up to isocyanate and try to get an amine. Once you get an amine here, this will learn it as an isomerization reaction in alkynes. That if you have NH2, OH will continuously keep adding onto it, so that this will become N minus, triple bond will keep coming, and finally it will end up getting into cyanide form. Okay, that's how you will get a cyanide form here. Okay, clear beta? Hmm. Right. What are reactions which look exactly similar, or they are very similar to HBD reaction? See, first one being Curtius reaction. Curtius is, instead of using an acid derivative like amide, you're using acid chloride. Okay, and the nucleophile that you are using is azide. NaN3 is called azide. NaN3 means N3 minus will attack here, remove out this chlorine. So as it removes out, you will get this structure RC double bond O, N, N, and N. And this is the structure which you have. Again, this particular case is ready for Wolff rearrangement. You see, minus charge on nitrogen can make a double bond. So this bond will break, try to push it to nitrogen. As it pushes, N2 gas will come out. So notice this end side, we should always have a very good leaving group. So N2 is a very good leaving group. It will leave, you will get isocyanate. Next one, Lawson's reaction. Lawson's is, you take, instead of simple amide, you take hydroxyl amide. There is a hydroxyl group present on the amide. Then react with TSCl, tosyl chloride. On reacting with tosyl chloride, this H and Cl will be released out. You will get OTS. And if you recall, OTS is an excellent leaving group. Okay. So keeping this in basic medium, OH minus will take H plus. You will get minus charge on it, and you will get this form. Again, nitrogen will push electrons here. R minus will migrate on nitrogen. This bond will break because OTS is a very good leaving group, ending up isocyanate. This is called Lawson's reaction. Next one is Schmidt reaction. Schmidt reaction is, you take a carboxylic acid, you react that with hydrozoic acid. Hydrozoic acid can provide H plus more easily. So this lone pair will take H plus, and as it takes away, this will become OH2. OH2 is a good leaving group. N3 minus will attack. So what do I get? I'll get azide carboxylate. And just now we learned this. If you get an azide, you can make a rearrangement again. So you can see the same thing here. RC double bond of N3. So this minus charge will make a double bond here. R minus will attack on nitrogen. Bond will break here. N2 will come out. So isocyanate will form. Okay. Clear, beta? These are very similar to HBD reaction because they are doing the same job. Okay. They are trying to convert into isocyanate. Clear, beta? Right. See the next one. Reactions of amides. If I take an amide, react with lithium aluminum hydride. Lithium aluminum hydride will provide H minus, and that H minus will add here. This will go away and convert that into amine. So whether you take amide here like this, or if you have two nitrogens here with a hydroxyl group here, all of them will convert into amines. Clear, beta? Next, if I take carboxylic acid, react with SOCl2, PCl5, CCl3, POCl3. All of these are specifically for removing this OH and pushing Cl. And they will all favor via SN2 mechanism. Okay. SN2 mechanism would be like this, where you have lone pair attacking on PCl5. Okay. And then once one of the Cl minus will come out, this Cl minus will attack, this bond will come out. So this will not happen simultaneously. First, as you attack, the pi bond will shift onto oxygen. Then that negative charge will push here to remove out this product. So this is called as, SNAE reaction. That means addition, elimination. First an addition, then an elimination. So it is an SN2 kind which is happening via SNAE, means addition elimination reaction. Okay, clear beta? Right. This one we have studied in alkyl halides, Hunt's-Decker reaction. That is, if I take an acid, react that with moist Ag2O. Sorry, in the presence of moist Ag2O, okay, you would notice that it will convert into a silver carboxylate salt. So you can see, just like acid base reaction, here H plus and here O minus, that will come out as OH minus, right? And this will remain as RCO minus Ag plus. So what are we getting? Silver salt of carboxylate. And silver salt of carboxylate, when you react with Br2 in the presence of H nu, silver and bromine together will form AgBr precipitate, and you'll have R and Br getting connected with each other to give alkyl borate, and this CO2 will come out. That is the overall reaction that happens. And if you notice the mechanism, this salt bromine will attack on silver beta because Ag is present as Ag plus. So that will convert into AgBr. And the minus charge which is present, that will attack on the second bromine, which is Br plus. So this is the salt form which you will get. Okay. Now, once you get this form, in the presence of heat, oxygen and bromine will split into radicals like this. And once you get a carboxylate radical, you remember coal-based electrolysis. There also we removed out carbon dioxide. Here also it does the same thing. R dot will come, and R dot will react with Br2 to convert into RBr and Br dot. Okay, so that's how alkyl boron bromate is formed here. Girls, please check Hunsdiker reaction once. Honestly, mechanism is not asked, but you might need to remember one thing, that there is a precipitate AgBr. This CO2 is leaving, and R and Br will connect. Okay, R and the Br will connect. Okay, next. See, usually at the bridged position, we cannot have a carbocation forming a carb anion forming. Any of that reactions are highly unlikely to happen. But if there is a radical forming, that reaction can happen. So therefore, on the bridge position, if you have a carboxylate, you will still see the Hunsdiker reaction happening, and bromine is coming at that carboxylate position. Okay, beta. Next. This is another new reaction that you will notice for carboxylic acids. Okay, known as HVZ reaction. Hell, Volhard, Zelensky. Okay. What we are trying to do is, we are trying to put a alpha halogen. So what is an important condition? There should be at least one alpha hydrogen, so that that hydrogen is being removed and halogen is being attached. Clear beta? So this is how alpha carboxylic acid is present. For halogen to attach, we require small amount of red phosphorus with X2. X2 should be sufficient enough. Red phosphorus should be an initiated amount. That means a small amount. Okay. Then you will see this hydrogen is being replaced by this halogen. This is called HVZ reaction. Okay. How does the reaction proceed? Check. Red phosphorus with Cl2 will become PCl3. PCl3 with some amount of carboxylic acid will convert into acid chloride. This we just learned that Cl will go, OH minus will come away, and acid chloride will form. Now, here is the interesting part. This acid chloride can be imagined as if it has a small amount of enol form. That means this hydrogen is moving onto this oxygen and double bond is forming here. So it will exhibit small amount of enol form. And how this enol form is helping is, if you have chlorine present in the molecule, the lone pair from here will push, and the pi bond from here, that is from this carbon, it will attack on chlorine. So as it attacks on chlorine, you will get C double bond OH, and the Cl minus which is released, it will take H plus and it will escape as HCl vapors. So what did we get? Alpha halo acid chloride. We didn't get acid, but we got acid chloride. Okay. But likewise, I said, if you are taking, you got to take this red phosphorus or PCl3 in a very small quantity, which means there is yet a large proportion of acid is present. Okay. And now when you have a large proportion of acid in front of this acid chloride, this chloride will be left with this hydrogen. Okay. And sorry, this chloride will be removed out and this OH minus will come here. So this part will convert into an acid and this part will convert into an acid chloride. Okay. Now, I have given the mechanism here. You can check it out. Although it is not essential, but just check it out. Acid chloride is there. Acid is there. So the lone pair from here will attack. You will get O minus. And once you get that, this carbon now has O minus and one Cl also. So the lone pair from here, as it supports, the pi bond will shift onto oxygen. You will get this product. Add. As this double bond, oxygen will close it as a double bond, Cl minus will come, and that Cl minus will attack here, bond will break from this end. So that's what I have shown it here, and thus giving us acid chloride separately and alpha halo acids separately. Okay. Clear, beta? This is the last step of HVZ reaction. Honestly, mechanism is not essential. Directly you got to know at alpha position, I need to put chlorine. Now, if you notice, the slow step is always about this one, that is about formation of enol. That is the slowest step. So since it is slowest step, the rate of halogenation, whether you take chlorine, bromine and iodine, it will be still same. Okay. Quickly go through these two HVZ reactions here. What is happening? Once you have a product already, alpha halo product, you can react with aqueous ammonia. Chlorine is removed, ammonia will substitute. So that is going to be alpha amino acid. And alpha amino acids are proteins. Those are the basic compounds of proteins. Okay. If you have chlorine react with NaOH instead, so then this will become alpha hydroxy acid, which you call it as lactone. Okay. Sorry. If there is a chlorine existing and you react with dilute NaOH, because this is a chiral center, we expect this to go via SN2 mechanism, remove out that Cl2, and we should have inversion happening. Correct? Inversion of configuration happening. But instead of inversion, it will retain into a R group only. That means retention is happening. Why retention is happening, Vita? So when you are trying to make a reaction, first reaction should be acid base. So it will become CO minus and then Cl minus will go away. So in this CO minus, it will internally attack. The oxygen can internally attack from the backside, removing out this chlorine. Okay. So this is a product that you will get. But at the same time, because this O minus is attacking here and Cl minus is leaving, configuration momentarily got changed. But again, when the OH- back attacks, the configuration got retained. So if you have it in, you know, H2O, definitely it is going to give you major product as retention. And if you use dilute aqueous NaOH only, then you will get major product as S configured. Okay, that is final product in this case. Clear? So please go through the application quickly.